Hello, good morning, good evening, everyone. This is the second talk on OvS Offload. In this talk, we'll focus on details on OvS Offload layer design and the challenges we face with that. Reintroducing myself, I'm Hemal. I'm lead system architect of architecture team in our Ethernet controller product line at Broadcom. And then my colleague here, Harsha, who is our principal software engineer, who has been focusing on OvS offload solution and number of vSwitch offload software design. I'll kick off the talk and then Harsha will go in more details. So with that, let me go to the next slide, which is, so for this talk, our agenda is we'll introduce the OvS offload layer. Then I'll quickly go into a couple of areas, capabilities, and the registration aspect and the issues that we face there. And then Harsha will go in more details on OvS DPDK offload thread model issues. We'll cover specific challenges that I mentioned in the previous talk about two-bridge model for the tunnel decap and what challenges we face there. And then in the end, Harsha will cover partial action offload related design challenges that we faced in upstreaming the solution. And then provide an overview of differences between what we have with the user mode and kernel mode data path, and then summarize the talk. So with that, let's get into the talk. So this is a simplistic software layer view of OvS, all the way from OvS vSwitch daemon to the NIC. We are primarily focusing here on the control path. The data path you can see from the OvS DP provider and NIC driver. But in the control path, we have offloads that are provided through multiple sublayers. We call all of this together as offload layer. The offload layer is split between a generic layer and provider specific layer. And that's how the control plane is implemented. It is device agnostic. It is hidden from the OpenFlow protocol layer. And the flow APIs below those, which are supported by the NIC driver, it supports multiple of those. And we have seen RTE flow, TC flower, those supports different offload models as I discussed in the previous talk. Those flow of APIs are registered by specific provider. There are two subset of flow APIs that are important to this flow offload. The management of flow specific flows, put rate and stat. And then when you deal with the offloaded flows for dealing with the flow dumps, the create, destruction, etc. APIs. So that this is the focus of our talk. We will focus on this, what we call OvS offload layer and challenges we face with that. So the first one here with any offload, the general offload layer design is you have some built-in capability discovery, and based on that, the layer above it makes some intelligent decision. With OvS offload today, that capability functionality is almost non-existent. In addition, DPDK has at least RT flow validate call, which allows you to validate a flow before it's offloaded. That equivalent of that doesn't exist on the kernel TC flower mode. So this creates different kind of offload functionality. Not only that, it's not really optimized for the underlying device, what it supports, because not necessarily all devices support the same offload capabilities. So just by having some simple kind of bit mask, which allows a device to advertise its offload capability, and the offload layer intelligently using it can improve the efficiency. So this is one area where OvS offload layer can improve. The second one here is on the OvS offload registration. The registration model we have today is each provider registers with the data path specific flow API object. And this registration is done during the offload provider initialization, and those API objects are added to global list of APIs. Simple registration model, but there are some inherent problems with this. One is it assumes every device supports the flow APIs once the provider has been initialized. It doesn't do any device-specific check. And what this results into, when you enable hardware offload in OVS, then offload is attempted on every single ETH device attached to that OVS. So this is not efficient. So definitely there is room for optimizing the whole OvS offload registration process handled by OvS Offload Layer. So with that, let me take a pause here and hand it over to Harsha to go into more specific details on other number of issues and challenges we face. I'm going to stop sharing my screen, and Harsha will continue the presentation from here onwards. Harsha?
Yeah, thank you, Hemal. So just a second, I'll share my screen. Okay. Do you see my screen, Hemal?
Yes.
So I'll be looking at the OvS DPDK offload layer thread model and the related issues. So in OvS DPDK, there's a bunch of PMD threads that actually process the packets, handle data path misses, and the open flow classification, and so on. But then there's a separate thread that handles the offload request. It's called the offload thread. Because there is a separate thread, obviously there is some scheduling latency between the PMD threads and the offload thread. And also, the number of PMD threads could be varying and based on the number of devices and also the number of RX queues per device and so on. But all those PMD threads schedule the requests to one offload thread. So some kind of serialization goes on. Further, there's lack of error propagation from the offload thread back to the PMD threads. This is another issue. And further, if you want to, let's say, share some data between the offload thread and the poll mode driver threads, today there's no infrastructure to do that and no synchronization or sharing of data between them. So these are some of the issues with the offload thread model. Concurrency and overall synchronization can improve this thread model. So let me go to the next slide. Here we look at the tunnel decapsulation hardware offload sequence. And in this slide, actually, we'll go through the whole sequence. And also, this use case is mainly for a VXLAN decap flow going to a VF endpoint. So the encapsulated packet is received by the PF and its poll mode driver. There's a flow miss in the data path, and it gets resolved through an upcall to OVProto. And then the tunnel header is popped, and the packet is forwarded to the VXLAN vport through recirculation. Again, there's a flow miss on the inner packet, this time in the data path. It is also resolved through an upcall to OVProto. And once that is resolved, it is actually sent down to the VF device to be sent to the VF. The PF device actually loops it back through the VF to the VM. So finally, the first packet reaches the VM through this low path. So far, we have only looked at the packet flow. Now we will take a look at the offload. So we are still in the context of the inner flow. So the user data path then offloads the inner flow to the poll mode driver and the PF, that is arrows 12, 13, and 14. We then wind back to the data path in the context of the PF, and the user data path then offloads the tunnel outer flow to the PF. So that is arrows 15, 16, and 17. So when the next packet comes from the wire, it hits the offloaded flows in hardware, and the packet is switched directly to the VF endpoint. The next couple of slides go through this in more detail. I'm going to skip those slides. So this slide basically captures some of the hardware offload issues related to tunnel decap. So as we just saw, it actually involves two flows and also recirculation in OVS. Flow F1, which is for the tunnel outer flow, matches in the tunnel header fields. And the action is to pop the tunnel header and output it to the VXLAN vport. And flow F2, which is the inner flow, we match on some of the tunnel specific data like the tunnel ID, VXLAN VAD in the case of VXLAN tunnel, and also the inner headers like the inner Ethernet header. And the action is actually to output to the VF representative port. So essentially, packets cannot be processed entirely in hardware until both these flows are offloaded. That's one problem. And the decap flow offload sequence could be different. As we saw in the previous slide, typically it is the inner flow which gets offloaded first, and then the tunnel head, the outer flow. But then if for some reason, if you reject the inner flow F2, let's say it's an ARP packet and you don't want to offload it, if you reject that, then only F1 or the outer flow gets installed. And later, let's say an IP packet for the inner flow comes along, then only F2 needs to be offloaded. So these are some of the scenarios where the offload sequence could go different, and the PMDs cannot assume a specific sequence, and they need to handle this internally, the various sequences. Tunnel metadata handling is also a bit complex with decap flow sequence. When OvS software data path action handles the outer flow, the action is actually tunnel pop. So software data path actually passes the tunnel header as metadata to the next stage. But in the case of hardware offload, we can't really pop the tunnel header when F1 is offloaded, because otherwise you end up losing the metadata if you need it for this F2 or the inner flow processing, because we match some of the tunnel specific data in while we match on F2. So if there's a hardware miss on F2, then the packet, if the packet is already decapsulated, when there's a miss on F2, we need to punt it to OVS for software data path handling. But then if you have already popped the tunnel header, then OVS won't be able to process it. So that's one of the challenges. Similarly, we have some issues with the statistics handling also, because for the same scenario, when there's a miss on F2, but actually it's a hit on F1, so hardware would have already counted in hardware for F1, but then when we punt it to software, we cannot double count it in software, the flow F1. Further, there's mapping required between the vport to the physical port. This is in the context of the inner flow. Because we are in the context of a virtual VXLAN vport, we need to offload the request to a physical port or uplink port. But then today, there's no mapping to figure out what is the actual physical port through which the packet came in. So there are some challenges here that we need to manage. So overall, the OVS two-bridge model for tunnel processing makes this decap offload a bit more complicated. Let's go to the next slide. Okay, in this slide, we look at the OVS DPDK action offload challenges, specifically the partial action offload. Today in OVS DPDK, we have partial offload, which is basically classification offload. We offload the match part of the processing to the hardware. This is typically done when you have a software port like a VirtIO or a vhost user port and a hardware port involved in the flow. We want to extend that and make it really offload real actions like tunnel encap, decap, VLAN, push pop, and so on to hardware, so that hardware both classifies and executes a bunch of specified actions. But the challenge is partial offload is today supported only on the ingress device. There is an assumption that the offload should be done on the port on which the packet is received, and if it happens to be a hardware device, the offload is done. But we don't really consider a scenario where there is one software ingress port, but the egress port could be a hardware port. Also, the deferred offloading that we saw in the earlier slides, where there's a separate offload thread, that creates a slight transient out of sync condition where though the action is offloaded to hardware, it takes a while for the PMD threads to see that state when we introduce some kind of state between the two. And the PMD threads might continue processing these actions even after the flow was offloaded for a little longer. And today, there is some lack of APIs to determine whether a flow is eligible for partial actions offload. We need to extend some of these APIs. That's another challenge. And also, we need some kind of assistance from the data path. For instance, this partial action could be supported only with OvS DPDK, which is the user data path, and we may not initially support this with kernel mode offloads or PC offloads. So some kind of data path assistance to say whether a particular action is supported for partial actions is needed. So overall, the OvS data path and offload layer designs are not very friendly to partial actions offload as of now. So this slide, we take a look at the various key differences between user and kernel mode data path and offloads. For instance, in kernel mode, there are handler threads that actually process the flow miss and upcall. In the user mode DPDK, there is PMD threads that process the flows, and they process the flow miss and upcall too. The flow is added to either the kernel data path or if it is offloaded in the case of kernel mode. In user mode, the flow is always added to the data path and it's also offloaded. The offload is attempted first in kernel mode. If it fails, we go to the DP. In user mode, it's added to DP first and the offload is scheduled. In kernel mode, the offload is synchronous. Handler thread waits for the offload to complete. In user mode, as we saw just now, the offload is async. It is dispatched to an offload thread. Offload errors are returned to the initiating thread in kernel mode. In user mode, there is no such, today, there is no such facility to propagate the errors back. Dynamic rebalancing is supported in kernel mode, and user mode lacks dynamic rebalancing support. There's a single flow table in the case of logical, at least, in the case of kernel data path with no issues of duplicate flow. Whereas in user mode, the flow table is actually per port and per PMD. Each PMD has its own flow tables, the data path. So offload layer has to manage this duplicate flow adds. So overall, there are inconsistencies between user and kernel modes that we need to take care of. So this is the summary slide. So as we just went through all these slides, you can see that OvS offload layer design is a bit complicated. Offload capability and discovery is fairly primitive. Serialized threading model poses some challenges for partial actions. And the two-bridge model poses some challenges for the kernel decap offload. There are differences between user and kernel mode offloads that need to be reconciled. Overall, it is still somewhat is still needed redesigning OvS offload layer. So with that, we come to the end of this presentation. Thank you. Thanks, Hemal.
Yeah, thanks, everyone. And that concludes our talk here.